What's up? This is super awesome Physics Lab 6, magnetic molasses. My name's Cole. Um, this is just basically we wanted to analyze magnetic induction and induced currents by dropping a bar magnet down a tube of aluminum foil, and just kind of see how the magnet interacts with the aluminum tube. Um, so we basically just did it experimentally as well as modeled it computationally in GlowScript. And as you can see, the times were slightly different. Don't worry about that, it's chill. Experimentally, we averaged 1.308 seconds, and computationally, it's simulated to be 0.715. Um, you'll see a bit more about how we modeled that and how the experimental times were derived as well. So procedure-wise, we use the magnetic dipole moment in computational calculations from the previous lab. We took the mass and tube measurements of really everything. Then we basically dropped the magnet down the tube 5 times, filmed it, and then took the time from the film so it was a bit more accurate instead of manually using a stopwatch. System was magnet and tube, surroundings or everything else, initial conditions, velocity 0, stationary, length of the tube 0.3 meters, time is 0, obviously. So main physics principles. The dipole magnetic field, kind of a freaky formula. This is really only used in the computational calculations. Biot-Savart law, this is for basically the induced current. Um, Newton's second and third laws, we use those for acceleration as well as just finding the force of gravity. And then Faraday's law is cool. I don't know. These images are from the computational model. And you can see, it's going to see the dipole of the magnet moving down the tube as time goes on. That's the dipole, obviously north end at the bottom, south end at the top, drop down. Mass of the magnet, 0.025 kilograms. Really cool number. Whatever. Mu of the magnet, 1.9008. That was derived from the last lab. We're just carried over. Couldn't really want to find that again, so we just assumed it's the same. Tube length, 0.31 meters. Width, ooh, I think I wrote this down wrong, but it was 0.31. Width 0.1, that it's meant to be 0.1. Or no, it is. Okay, I take it back. Spouting nonsense. Inner radius 0.02, outer radius 0.03. These are our trial times. So of the 5 videos, we basically just like timed it within the video, noted down the times with the average 1.308. Velocity versus time. This is from the model we created in GlowScript, or I did, not we. And so you can kind of see the magnet speeding at the terminal, staying at terminal, and then at the end, just freaky stuff. This is my code. I really just input all my constants and stuff from the starter code that was given to us. Nothing really crazy. If you have any questions, I guess pause the video and then comment that out. What if? What if the resistivity of the conductor were reduced to as close to possible to 0? How would the dynamics of the following method change? Well, as resistivity decreases, I mean, there's less resistance, so there's more current, and that can create a higher magnetic field. So with a greater magnetic field becomes more force, and therefore the magnetic, the magnet will slow down. If it is in a just big ass field, with a ton of force slamming against it as it tries to go down, it's not really going to go anywhere, and so it will slow down. What if there are holes or slots in the tube? How would it affect the ring? Well, if there's holes, the current doesn't really have as good of a place to flow through, and so there's disruptions in that field that it's created, and basically the magnet can fall faster because there's not as much force resisting it. Error and deviations. So obviously the computational time and experimental time were a bit different, up at like 0.6. The computational time isn't exactly accurate because assumptions were made, which I'll go over in a second. But experimentally, it also could have had errors where it was bumped against the wall, didn't drop it directly in the center. The inside of the tube wasn't exactly a smooth surface, so it could have been just jostling around and hitting the walls a bunch. And then assumptions for the computational model, we treated the bar magnet as a perfect dipole. There's negligible air resistance, and no other forces besides magnetic gravitational were used. Yeah, and I mean, I kind of went over the other things, so anyway, have a great day. Good luck on exam 2, or 3.